Gnanam Paramam Dheyam. Knowledge is supreme.
So, in the last lecture, we have seen for each polynomial we have attached a Galois group, and we are studying zeros of this given polynomial in terms of the action of the Galois group on the zeros of that polynomial. So, let me go on this furthermore and give little bit more information, more intimater statements. So, I will assume now f is a monic polynomial which is a product of finitely many prime polynomials distinct. So, and each this is a polynomial in Kx, K is the base field, and pi 1 to pi r are distinct prime factors. In Kx, and they are all separable and separable. So that means they don't have repeated zero, therefore f is also separable. So f is also separable. Then we have attached a field to this, that is L, which is a splitting field of f. So adjoin all the roots, they call them to x1 to xn. This is the splitting field of f. Over k, and then therefore we have this extension L over k, which is the Galois extension because it is normal and separable, and therefore there is a Galois group, Gal L over k, and this is how we have defined it to be Galois group of polynomial k over polynomial f over k. And we are studying operation of this Galois group on the roots, right? And the last time we see, so operation of Gal kf on Vf, which is x1 to xn, and therefore the action homomorphism is a group homomorphism from Gal kf to the symmetric group on this x1 to xn, and this map, this is a group homomorphism, and this is injective. Injective simply because each element sigma here is uniquely determined by the tuple sigma x1, sigma of xn. If you know the values of sigma on x1 to xn, then sigma is uniquely determined. That simply means this map is injective. Therefore, one realizes this Galois group of f as a subgroup of Sn. But this homomorphism, this one, depends on the numbering we have chosen x1 to xn. If somebody else chooses the different numbering, then this group will be corresponding conjugate subgroups, because the different numbering will give you a permutation, and that will be conjugation by that permutation will be the image will differ by that conjugation. So, and last lecture we have proved that the orbits are precisely v of pi 1 etc., v of pi n, pi r. These are the orbits. So, the roots of pi 1 will be permuted among itself, pi 2 will be permuted among itself, and so on. So, they will not meddle with each other, because that is how the algebraic structure of f is preserved under the operation. So I want to write down the corollary, one more corollary. Under the above notation, more finer statement, that is Galois group of F over K. To now, the earlier it was in the group Sn, but now it's I am taking the permutations on the roots of pi 1 cross permutations of the roots on pi r, and then sigma goes to this. So sigma will permute these guys. So sigma is giving a permutation here. So that is so it's not, I didn't number it, so it is clear that this is this sigma gives a permutation by sigma of if you call the roots of pi 1 to be x11 sigma x1 nu 1. So there are nu 1 roots for pi 1. This is this tuple, this permutation, and so on. So you get here R element. So note that this group is not isomorphic to, this group is contained in S of x1 to x1. This also has the same letters, but this group is, see, for example, you take S4 and you can take this card. So S4 may not be a right example. So what I am saying is, if you take S2 cross S2, so this one has cardinality. So this is also these two letters. This is also contained here, but not equal. This one permutes only the two fixed letters. This one permutes two fixed letters. So this one is abelian, for example. This is not abelian, and so on. So therefore, this is better, finer information than that. And here also the comment again the same, that this group homomorphism, this is a group homomorphism, and it's injective. Injective for the same reason, because sigma is uniquely determine the values on all these guys. Therefore, it is injective group homomorphism. So, for example, if you know it is S2 cross S2, then it is abelian. Before I do, I need one more observation. That let me write that observation. So, this is a proposition. And now I will assume K is a field, and I will assume characteristic K is not 2. And F is a polynomial which is monic, and it splits into these prime factors, and each pi 1 to pi r are separable prime polynomials. In Kx. This, then I want to know, so we have seen above that Galois group, so this Galois group, we know this is a subgroup of Sn, a subgroup of the symmetric group N, where N is the number of roots, N is cardinality of the roots of F in the algebraic closure, and that we write this set as x1 to xn. They are distinct roots, as many as the degree of F. Degree of F is n. Okay, so now I want to know when is this group contained in the alternating group. So I want to know this. So this is always. So this is always. So then this Galois group is a subgroup of alternating group An if and only if the discriminant DISC. Now I write this notation, discriminant of f. We have seen the discriminant is a constant. Like in a quadratic case, it was b squared minus 4c. So this is in k. That was we approved this. But this is contained in n if and only if discriminant is a square in k. Just not in k, but it's square in k means what? So that means this discriminant of f is some a square for some a in k. This is what the statement is. So, let me first give a small example to why it is useful. So, for example, this is a very small example. This should be done in the school. You do it in the school. So, example, we take a degree 2 polynomial f. F is x square plus bx plus c. This is the polynomial. And in this case, we know what is the discriminant of f. Discriminant of f is b squared minus 4c. Okay. And suppose this is a square. So if the discriminant of f, if this is a square, if this is a square in k, what does that mean? Then that means b squared minus 4c, this is some a square for some a in k. That means I know the root then, and therefore the square root of, when I write b squared minus 4c is plus minus, this is same thing as plus minus a. So that means this polynomial actually splits into linear factors, x plus a and x minus a. And where are the factors? They are in kx. Because this is a in k, therefore the factors are linear. So that means the original polynomial you started with, it actually splits in k only. So therefore what is the splitting field? This is nothing but k only. Because the polynomial already splits in k. But then what is the Galois group? What is gal k over f, gal f over k? This is nothing but, it's a group. And what is the extension? It is a trivial extension. So Galois group is trivial. Only identity. So this is very easy. Converse is also correct. Unconversely also. Same steps. So therefore a quadratic polynomial can have, so what are the possibilities for the Galois group? Let us write it down. So we have proved Galois group over k of a quadratic polynomial. Degree f is 2. Monic you can always assume. And more importantly, characteristic of k is not 2. Then there are two possibilities, and we will write down exactly when is which. This is identity, trivial. If discriminant of f is a square, so that means it belongs to k2. Remember, k2 is all squares. These are all those a square such that a is in k. All squares. That is, then it is identity. Otherwise, it will have, what will be the splitting field? If it is not a square, then it is contained in n, that or the proposition I stated. But that means in that case it will be S2. There are only two possibilities. If discriminant is not in K2, not a square, so it is not in A2, therefore it has to be in S2. But if it is not in A2, is a trivial, this is a trivial, this is the group A2. So it's, and one can do such analysis for degree 3, degree 4, etc. But then all that you need to compute the discriminants. So then it becomes a computational, that becomes precisely theory of equations. Alright, so let me prove the theorem I stated first. So discriminant, so I want to prove this. Galois group is contained in An. We know it is always contained in Sn in our setup. This is contained in N if and only if discriminant is a square in K. In K is very important. Alright, so proof of the theorem. Proof. So let me recall a little bit about the discriminant. So recall that, so a polynomial f, this has degree n and it's monic. So x power n plus lower degree terms plus a0, and then what is the discriminant? So then you find a bigger field L, so go to the splitting field L of f, and there you write f as x minus x1, x minus xn, and this is in Lx. This L is a splitting field, kx1 to xn, and this x1 to xn are the zeros of f. They are all zeros and they are all distinct. Then what is the discriminant? If you remember, discriminant of f is nothing but you take the Vandermonde of x1 to xn and square of that. Now remember that this square, this Vandermonde is not in K. A priori this is in L, so this is in L2. This is a square in L2. This is always, this is what the discriminant is. How, and we have also proved that this actually belongs to K, that we have proved. And how did we prove that? We proved that this by using the following. If I have a sigma, an element in the Galois group, then sigma of V, let me just simply write this as V. This is nothing but sine of sigma V. So this Vandermonde, when I apply a permutation, what comes out is the signature of the permutation. So when will this Vandermonde be invariant? So V square is because of this. First of all, note that because of this, sigma of V square equal to V square. So that means V square is indeed in the fixed field, and fixed field is K because it's a Galois extension. This is a fixed field of under the Galois group, which is K because the field extension is Galois. So V square is definitely fixed. So V square is an element in K. That proves this discriminant is indeed an element in K. But by definition it was in square in L. But now the problem is, when is it square below? Alright, so this shows that. And where did we use characteristic? So here we have used the fact that the characteristic is not 2. Otherwise, sine of sigma is either 1 or minus 1, and minus V will become V. So there will be a trouble. So characteristic is not 2 and V is non-zero. V is non-zero we have used because these roots are distinct. So that is where we have used distinct, and characteristic is not 2. So therefore this shows that the Galois group of K of F in over K, this is it contained in An if and only if V is fixed under every element of the Galois group. But that means, so that implies this discriminant of F, which is V square, So it's v square and v is in, this is k, v is in L, therefore this is in k square. Conversely, if it is in k square, v and discriminant, the whichever square it is, that and v will differ by only plus minus sign, and therefore it's if and only if. This is if and only if. So we have proved the statement that if you want to check about the whether G Galois group is contained in the alternating group, we have to compute the discriminant and we have to check it is square or not square, and that we have seen in a quadratic case. Now let us do little bit more. So for example, so some couple of examples so that you will know what is needed to be calculated. So first of all, some examples at least. So one, I look at the polynomial f, which is x4 plus px plus p, and p is a prime number, p prime. Let's assume that p is bigger or equal to 7. Okay, and now observe. First thing you observe that f is irreducible over Q. Now, if you like, this is Eisenstein's criterion. Use that. Because I will apply to this is prime, the monic, both these coefficients are divisible by P and the constant term is not divisible by P square. Therefore, this is irreducible over Q. Alright, so and second thing you need to compute is you compute the discriminant. Now, how do you compute the discriminant? This is 4. So, discriminant is some determinant. You know, it's a van der Mode. Of course, you cannot hope to calculate discriminant by using the van der Mode, because if you want to use van der Mode and square it, then you have to know what are the roots. So, you have to have different techniques to compute the discriminant. So, computation can be done as follows. So that I want to explain. How do you want to do computation? That I will explain soon or maybe in the next half. And I will write down the answer here. The discriminant one computes is minus p cube 99p minus 64. So the discriminant is therefore negative. So it cannot be square. So cannot be square. And our base field is Q. Therefore, what do we infer? We infer the Galois group over Q of this polynomial x4 plus px plus p. This is not contained in A4. Because if it is contained in A4, the discriminant will be a square, but it is a negative, therefore it is not contained in a square. And from here, you conclude the Galois group over Q x4 plus px plus p, this has to be S4. So we have computed from here to here to do the calculation. Calculation means what? This is not contained in A4, so it has odd permutation and so on. And so standard finite group theory, you can conclude it's a transitive group, because we know the polynomial is irreducible. So this group is a transitive subgroup of S4, and therefore you conclude from there the group has to be S4 only. So this was one. So second example, you take the polynomial x4 plus x plus b, and b is some integer, b is an integer, and I want to calculate the Galois group over Q. So again you compute the discriminant of f, this is 256 b cube minus 27, which is what? Which is now it will depend on b. If b is negative, it's definitely, so if b is negative, it is definitely negative. If b is positive and big, then big means it's compared to this. So therefore, what answer you will get? You will get answer, it is either S4 or A4. And A4 this A4 will occur only for finitely many B's. So this B, only for finitely many B, it will be A4, otherwise it is S4. Because if B is negative, first of all, this is negative and therefore it can't be square, therefore it is not here, therefore it is here, and so on. So in all these examples, the most important thing now is a computation of a discriminant. That is what is very important. And in the next lecture, I will indicate how do you compute the discriminant, and it is not so difficult, but one has to use the linear algebra more effectively. That is one thing. Another thing is I want to mention here is I will make a definition here. So an extension, a Galois extension L over K, finite Galois extension L over K is called abelian if the Galois group is abelian. So, and I will keep calling Galois abelian extension. Abelian, if I write L over K abelian, that means it's a Galois extension plus the Galois group is abelian. So this adjective here which you are attaching, that is to coming from the group. So for example, if I say Galois group is non-abelian, so non-abelian extension if I say, that means it is Galois extension and the Galois group is non-abelian. If I say solvable extension, that means the Galois group is solvable, and so on. If I say cyclic, then the Galois group is cyclic. And one can write down a characterization of, so I wanted to write a theorem also. So L over K extension, Galois extension, then L over K is cyclic if and only if. This I will do it in the next lecture, and also we will know how to compute the discriminant. Thank you. We will continue after the break.